In this paper, we describe a two-level statistical model called motion texture for synthesizing character motion that is statistically similar to captured human motion. A motion texture is a two-level statistical model. Motion texture is learned automatically from motion capture data. Each texton is represented by a linear dynamic system, or LDS. Several segments can be represented by a single texton. The distribution of textons is represented by a transition matrix. Given a learned texton in initial poses, we can synthesize a motion sequence frame by frame by simply drawing samples from the noise term. However, the dynamics may deviate from the original one as time progresses, as shown in the middle sequence. We fix this problem by setting the end constraints of the texton, as shown on the right. On the left, when two segments are synthesized from two textons and concatenated together, a jump is visible at the transition. On the right, the transition is smooth after we impose end constraints for the first texton. Here we show another example. Cyclic motion can also be synthesized easily. Motion at each cycle is differently sampled. From a single texton, we can synthesize characters with fine details while keeping the same dynamics. Fine motions can be edited at the texton level. For example, we can change the pose of an intermediate frame of a texton. By setting the new pose as an additional constraint, new motion can be synthesized easily. With the learned texton, we can not only synthesize the original motion, as shown on the right, but also extrapolate new motion dynamics. Simply linear interpolating to a longer sequence would have slow motion effect, as shown in the left. Our algorithm extrapolates dynamics well, as shown on the right. Given two textons, our algorithm automatically finds the optimal in-between texton path.
We describe a system capable of robust, real-time learning and training for synthetic characters. Here we show an example creature built with our system. The pup naturally experiments with different behaviors from its behavioral repertoire. We interact with the pup using this pair of hands. The pup can be trained using a technique for real animal training known as clicker training. This click acts as a reward marker, pinpointing the performance of a desired behavior. In real dog training, the click is associated with receiving a food treat. If we click whenever the pup sits, the frequency of the sit behavior will increase. Once the pup is sitting frequently, we can begin to associate a verbal cue. with the performance of the sit behavior. Let's look behind the scenes to see what is involved in this kind of learning. The pup's behavior system is composed of a number of basic action tuples. Each action tuple has a value associated with it. When we reward the performance of an action by clicking, the value of the action goes up, and the frequency of its performance increases. Once an action has obtained a sufficiently high value, it becomes a candidate for a process that we call innovation. If we reliably associate a cue with this action, a new action tuple is created. This new action tuple will only be performed in the presence of the cue. This pup has discovered a new relationship between perceptual states and actions.
Sit.
This is an example of state-action space discovery. In performing this kind of learning, the pup has also discovered a new cue, the utterance sit. This is a state space discovery. The pup represents these cues and the rest of its world using a structure called the percept tree.
Good dog.
For example, whenever the pup hears a sound,
Beg.
his speech percept becomes active.
Sit.
The pup represents and classifies auditory patterns within this
Sit.
perceptual framework. Now we'll take a closer look at a typical training session. This graph shows the frequency of the pup's actions while interacting with the trainer. Before training, the pup's actions are equally frequent. As we begin to reward the sit behavior, its frequency increases. As we introduce the verbal cue, the frequency of spontaneous sitting decreases, while the frequency of sitting when we say sit stays high. If we stop saying sit, the pup behaves as it did before training. When we resume our vocal command, but stop rewarding the pup will gradually stop sitting in response to the cue. Finally, we'll look at some examples of action space discovery. The pup can be trained to perform actions through a process known as luring. During luring, the pup tries to follow the hand with its nose. Thus, we can guide the pup's exploration of its motor space by moving the hand. In addition, if we reward a novel motor trajectory, a new top-level action is added to the pup's behavior system. This new action can be subsequently associated with a verbal cue, just like any other of the pup's actions. For real animals, the form of an action is often very important. We can teach the pup the correct form of an action through a process known as shaping. Here, the pup naturally experiments with different forms of its shake behavior. If we reward the pup for higher and higher versions of this shake behavior, he will soon learn to shake high reliably. In this video, we have shown a character who possesses the ability to learn at a number of different levels. We believe that the ability to learn in these ways adds a new and rich dimension to interactive synthetic characters.
The following sequences depict one-syllable words, two-syllable words, short sentences, and longer sentences generated by our system.
All, badge, dwarf, jam, name, safe, dagger, endorse, gateway, iceberg, mammal, tabloid, the meeting was frank, 53%. More news in a moment. It's a matter of money. That's all for tonight. It could take months. The fire is being allowed to burn itself out. He tossed in 31 points and 11 assists. Warmer temperatures are predicted in some areas.
The following sequences depict other types of output generated by our system.
This video shows our process for motion capturing cartoons. Cartoon capture tracks and retargets the cartoony motion to any new medium, such as cartoons, 3D models, or photographs. In contrast to standard skeleton-based motion capture techniques, we read the motion of traditional animations by measuring deformation parameters. This includes the expressive movement created by the animator. In this simple example, we can capture the style of the animation by measuring affine motion parameters and then reapplying these parameters to a new image. Now the donut bounces like a beach ball. As the images become more complex, we capture key shape interpolations. For each frame, the red point shows how close the frog is to each key shape. To retarget the motion onto a new character, we replace the frog keys. This allows us to recreate the original motion style, but now it is on the bunny rabbit. Here you see the full process for a new animation. The motion is retargeted to a simple drawing of a flower. This technology could be employed to build a cartoon capture machine, which transfers motion from cartoons onto ordinary characters, who then take on the attributes of the source material. Just imagine the possibility.
This is a demonstration of the Sage graphics architecture. These video clips were filmed in real time from prototype Sage hardware. NTSC format is not the best medium for proving photorealistic image quality. However, it can show the presence or lack of temporal artifacts and give some flavor for the realism of these anti-aliasing results. All of these sequences were rendered at 640 by 480 interlaced video with a 30 Hz frame rate. No special processing for interlacing was performed. In this video, we will show real-time control of our hardware architecture for anti-aliasing. First, we show an un-anti-aliased segment of a bee comprised of 176,000 triangles. The geometry of the hair is particularly difficult to render without bad aliasing artifacts. In the next segment, we show a 1/3 Mitchell filter. The bee is a true torture test for anti-aliasing algorithms. The hair on the bee is considerably less than an NTSC pixel in thickness. In the next segment, we demonstrate that the filtering is happening at video rates. We are dynamically changing the filter parameters tied to the position of the mouse. You'll see that the mouse position controls the sharpness of the filter. In the next segment, we use an edge enhancement filter called the Laplacian filter. And again, the parameters of this filter are tied to the mouse position. Notice as we pass through certain regions of the screen with the mouse that the edges are extremely enhanced.